Okay, good morning. This is Professor David J. De Los Reyes. The date for this morning is May 2, 2023. Okay, it's past 10 o'clock in the morning. Okay, my new topic and my long-form video for this morning will be Newton's method of approximation. This is the so-called systematic trial and error method of finding the roots of any given function of x. Okay, I will check the camera. Oh, it's fine. So my new topic on my long form video, and it's still under advanced mathematics, Newton's method of approximation of solving the roots of transcendental equations. Transcendental meaning equations beyond ordinary. Okay, it's more complicated than the ordinary one. That's why we call it transcendental equations. Okay, let's bring out the concept of a Newton's method of approximation. This is now advanced math, lesson 35. Newton's method of approximation of solving the roots of transcendental equations. Transcendental meaning equations beyond ordinary. The concept is something like this. It is used for finding roots of equations containing transcendental terms. I just repeat it, okay? The equation will be something like this. X2 will be x1 minus the ratio function of x1 all over f prime of x1. The meaning of this, if we are given a function of x, okay, and the problem is asking for the value of x, okay, the equation should be transcendental. It is beyond ordinary. You cannot solve this by just simply using the laws of exponents or other things. So we must have to use the so-called Newton's method of approximation. If we are given function of x and the problem is asking for x, on the first assumption, we will assume a value x1 originally. We'll substitute it on the given equation. If what comes out in the equation, it satisfies the given equation, okay, that will be the solution. But just in case you put x1 on the given function of x, and what comes out will be a +1 or a -1, something like that, there is an error on the assumed solution. So to compute for the next possible roots, this will be the equation. That is x2 equal to x1 minus the ratio fx1 over f prime of x1. The meaning of f quantity x1 is actually the value of that given function of x when x1 assume that x. That's the meaning of this. That's why I place it here. x1 is the first trial value of the root. Okay? And x2 will be the next possible solution. That's why to compute for the next possible near perfect solution, we will use this equation, that is x2 will be equal to x1 minus the ratio of function of x1 over f prime of x1. We are given x1, we could compute for function of x1, and we will compute for the first derivative of x1, meaning if we are given the first derivative of the given transcendental equation, okay, we will substitute the original value of x1 and we could compute for the value of that. Okay, so just take the ratio of this, you subtract it from x1, that will be your new solution, which is nearer the exact solution. So this is very important. That is, under Newton's law of approximation, x2 will be x1 minus the ratio function of x1 over f prime of x1. Okay, I will check my camera again. Oh, it's still fine. So function of x, okay, is the value of the function when x1 is substituted. F prime of x is the value of the first derivative, meaning the first derivative of the given transcendental equation. The value of the first derivative when x1, this should be nothing. When x1 is substituted. Okay? So you now know the significance of this, f of x and f prime of x. We put x to that given x, we could compute for f of x. We put x for that f prime of x, we could compute for f prime of x. So just take the ratio of this, you subtract it from the original x1. So the nearer perfect solution to the unknown is actually x2, and we could compute for it. So if the resulting value of x2 or fx1 is approximately equal to 0, okay? Meaning there is no error. It's not either plus or minus, meaning the solution is correct. Okay. Let's try to bring out an example using Newton's method of approximation. We'll bring out an example so we could visualize it. Okay, the given example, I will give you example number 1. The given example is x to the x minus 5 equal to 0. You've been watching short videos on short form videos. I think no matter what we'll do, you could not use the laws of exponents here. Okay, so the proper solution should be by using Newton's method of approximation. Newton's method of approximation is actually what is called the systematic trial and error solution. Hold on. Okay guys, let's continue. Example will be x to the x minus 5 equal to 0, find for x. Okay, let's try to bring out the proper solution of this using Newton's method of approximation. For the solution of this, we will let y equal to x to the x minus 5. Okay. Y plus 5 will be equal to x to the x after the transposition, taking the natural log of both sides. The natural logarithm of the quantity y plus 5 equal to the natural logarithm of x to the x. Taking the derivative of both sides with respect to x. The derivative with respect to x of natural logarithm of y plus 5 equal to the derivative with respect to x of the natural logarithm of x to the x. Differentiating. This is 1 over y plus 5 times y prime, that is dy dx, equal to the derivative with respect to x. We could simplify this one to be x natural logarithm of x. So if we try to take the differential of this, okay, it falls under product. First function, second function. So it should be x, and the derivative of natural logarithm of x with respect to x will be 1 over x times 1. We are differentiating with respect to x. Plus the second one, natural logarithm of x, times the derivative of x with respect to itself, this is times 1. So simplifying this one, y prime over y plus 5 equal to x and x cancels, right? So this will just be simply 1. So what comes out on the right hand side will be natural logarithm of x plus 1. Because this x here cancel with this. This, what remains here is 1. So computing for y prime, that f prime over there, it should be the natural logarithm of the quantity x plus, natural logarithm of x plus 1 times, we put this one on the right, times the quantity y plus 5. Or y prime now will be the natural logarithm of x plus 1 times the quantity. What is y? Y is actually x to the x minus 5. Right? So this is x to the x minus 5 plus 5. So actually this cancels. So the first derivative of the complicated transcendental equation will be x to the x times the quantity natural logarithm of x plus 1. Why we have computed for this one? We have computed for this one because in the computation of the second root, we needed that one. Right? So if we try to solve the value of x now, we should know the upper and lower limit. The lower limit. For the value x to the x minus 5 equal to 0, if x equal to 2, 2 to the second power will be 4 minus 5. Okay, so there's a difference actually equal to minus 1. Since this is minus 1, the assumed lower limit is actually a lower value. If we assume x equal to 2.15, we put x to be 2.15 over here. The difference will be, what comes out? 2.15. It is around 5.18 something. No. Lower limit. 2.147, something like that. Okay? Since this is not 0, the value x to be 2.15 is actually higher than the correct value. So our solution should be between the limit, okay, between 2 and 2.15. So we will assume that the value of x will be between 2 and 2.15. Right? Okay. We'll compute for x2. x2 will be 2 minus f1x is actually negative 1 over 6.772. Okay? What comes out is actually 2.147. This should be plus. Okay? If we compute for, if we substitute the value of 2.147 back here, the difference is actually 0.15. You see it? It is 0.15. It is not 0. So meaning, the value 2.147 is higher than the correct value. Okay? And if we compute for the value of x3, the next possible root, x3 now will be 2.147 minus the ratio fx2, 0.15. The value f prime of 2.147 is 9.098. This is plus 0.15 over 9.098. So the value x3, the assumed trial value x3 will be 2.13 if you try to simplify this one. Okay? It is 2.13. And if we place 2.13, y to the x, 2.13. The value is approximately 5.0 something, and the difference is actually 0. So the correct answer for the value of x will be x equal to 2.13. So our assumption that the answer is between 2 and 2.15 is actually 2.13. Because if you place 2.13, y to the x 2.13 over here, 2.13 raised to 2.13 minus 5, what comes out is actually 0. So the value of x is actually 2.13. That is only after taking the third trial. That is the so-called Newton's method of approximation for solving transcendental equations. Transcendental equations are actually equations beyond ordinary. It is a systematic trial and error method of solution. Okay guys, so for those of you who are taking advanced mathematics, this is Newton's method of approximation of solving transcendental equations. It is a part of advanced mathematics. So if you want to subscribe to my channel. My channel is at youtube.com/@proofdavidj.de. And if you want to share it, please click share. The answer here is 2.13. 2.13 raised to 2.13 is 5. So 5 minus 5 is equal to 0. The difference is 0. So actually, on our third trial, okay, when we put the value of x to be 2.13, the difference is 0. So the correct answer should be 2.13. Good morning from Los Angeles.